Hello everybody, this is Dr. Christopher White and welcome back to Sedimentary Rocks Part 2, Part 1. Okay, so we have just been discussing river sediment, so fluvial systems, and now we're going to move on to desert environments. So obviously a desert environment is going to differ from a river system quite obviously by the fact there's very little water moving around. So in the case of a desert environment, the wind and gravity tend to be the main driving forces behind sediment transport. So your average desert environment has three sub-environments in it. The first one are the sand dune deposits, also sometimes referred to as the desert plain. So this is the kind of classic image of the desert that we have, with the big sand dunes. But there are also a couple of other environments in your standard desert system. There's the alluvial fan deposits. These tend to be located where the desert plain meets areas of topography, so hills and mountains. And the hills and mountains are going to be the source of the sediment that's on the desert plain. And so where you have these desert plains meeting these areas of high topography, these are areas where you tend to get the short-lived chaotic rivers, and which will produce quite a poorly sorted, brecciated sediment, and which is seen commonly as alluvial fan deposits. And then in desert environments, we will also get short-lived bodies of water. So we'll get very short-lived lakes, which are referred to as Playa lakes. And so these lakes will form typically in the spring, and then they will obviously dry out, and so we'll get evaporites forming. So the desert plain consists of wind-blown sands, which will naturally form dune systems. Now the sand itself associated with these desert plains tends to be very well sorted, so the sand class have a very tight size range. They tend to be very well rounded, and the sand itself tends to be dominated by quartz. So sediments associated with desert plains are actually very easy to spot. They're very well sorted, very quartz rich, and the class tend to be pretty well rounded. And so you can spot that quite quickly. And most other environments where you have sand, so something like a beach environment, will not tend to have quite the same level of sorting and quite the same level of rounding. Obviously, we will also see crossbeds, which can be anywhere from meters to tens of meters in size, and these are related to the migration of the sand dunes. We discussed that in the previous lecture. And if we do have any fossils present, they'll be from land-dwelling plants and animals. The most common type of fossil we get in these desert deposits would be reptile fossils, which makes sense. Hot, dry environment, reptiles kind of like that particular system. So here's a crude diagram from the textbook showing the desert system. So obviously we have a high ground over here in green. This is going to be our sediment source. We have the desert plain itself here in yellow. The point where the desert plain meets the high topography, well, that's when we get the alluvial fans forming. And then we'll have these isolated short-lived bodies of water, these Playa lakes. Now there's also a sequence of muds which will occur along the edge of Playa lakes, which is referred to as the sabka, but we're not really going to worry about that too much. So okay, so here's a picture of Death Valley. So you can see straight away, here's our high ground to the west, and we have a line of high ground over here to the east. So this is going to be our desert plain here. Okay, so we have a high ground to the west, high ground to the east, and we're going to have our desert plain in the middle. Obviously, you can see here, this area looks quite smooth, doesn't it? So this is going to be our desert plain. And when you compare it to this area here, well, this area here looks a bit more complicated, doesn't it? Okay, you can actually see you have multiple channels moving through this area. This is the alluvial fan, or these are the alluvial fan deposits, should I say. So if we actually look at this particular alluvial fan, this is a beautiful example of an alluvial fan here. So what's happening is you get short-lived, fast-flowing streams that come down these narrow valleys, taking a whole lot of sediment with them. And obviously when that sediment and the water leaves the valley itself, it fans out onto the desert floor, producing this rather distinct lobe morphology. And so just imagine you have, dozens of these things all overlapping with each other. Well, then you end up with a line of alluvial fan deposits just like this. So here's our high ground. Here are our alluvial fan deposits there. We have some alluvial fan deposits here. We have an individual one there. We've got a few bit more here as well. We have our desert plain, and then we have this area of white looking sediment. So this is going to be our Playa lake. You can actually see what's left of the lake right there. That's, you know, the dregs of the lake there. The rest of the water's evaporated away, leaving behind the evaporite minerals as it's done so. So we have our alluvial fans there, we have our Playa lake there, and we have our desert plain there. And obviously we then have the high ground either side supplying the sediment into the desert system. So okay, so alluvial fans. So they form along the margins of the desert basin, where essentially the desert plain meets the high topography. So they're formed by short-lived river systems. And the rivers will flow down steep-sided canyons. Because they're short-lived, they're quite powerful. So you get a lot of water coming down very quickly, lots of, high velocity, high energy, bringing lots of sediment with it. Obviously, when the river exits the valley, it spreads out, and so the sediment fans out as it leaves the valley. And this produces this rather distinct lobe morphology, also sometimes referred to as a fan morphology, if you look at it in plan view. Now, if I were to take a slice through my alluvial fan, what I would see is it would actually have a more triangular shape, with the sediment being thickest here and getting thinner as you move towards the edge of the alluvial fan. In terms of the sediment itself, it tends to be very poorly sorted, because it's literally a case of whatever material is being washed down the river valley. It tends to have quite a lot of coarser material, sands, gravels, cobbles and boulders, but there will also be some finer clay and silt-sized material mixed in there as well. Now, this clay and silt-sized material doesn't tend to stick around for too long because it tends to get blown away by the wind. So most alluvial fan deposits tend to be relatively silt and clay poor, and they tend to be dominated by sands, gravels, cobbles and boulders. Now, because the sediment moving along the canyon hasn't been transported very far, it means there's been less time for the clasts to bang into each other, so they don't tend to be very well rounded. So you'll tend to find angular clasts associated with alluvial fan deposits. So the sediments we get associated with alluvial fans tend to be breccias. So if you remember, if the clasts are in excess of 2 millimeters in size and they're angular, it's going to be a breccia. Now, if your clasts are less than 2 millimeters in size, you're going to have a sandstone. And we get a particular type of sandstone associated with alluvial fans. We tend to get what's referred to as an arkose sandstone. And arkose sandstones are relatively easy to identify. They're typically a kind of rusty red colour, which reflects the fact they formed in a dry environment, like a desert or semi-desert. And they'll also tend to be quite feldspar rich. So the sediment that you get on your desert plain itself tends to be quite quartz rich, and that's because the sediment has been transported over very, very large distances. The wind is constantly moving it backwards and forwards. So over time, the total movement when you tot it up is quite large. Now this means that feldspar, even though it's a very, very robust mineral, it's very strong, it's 6 on the Mohs scale, because it's been moved around so much, it will eventually degrade physically and fall to pieces and be lost. And this means that desert sands will tend to be dominated by quartz, because over time the feldspar gets destroyed. In the case of a alluvial fan deposit, on the other hand, well, it hasn't been transported very far. That means there'll not only be quartz in your sediment, there'll also be quite a lot of feldspar. And so that means any sandstone that's forming as part of your alluvial fan system will be a mixture of quartz and feldspar. And so a very feldspar-rich sandstone is classified as an arkose sandstone. Okay, so what about the desert plain itself? Well, the desert plain is going to be covered in sand dunes. And a sand dune is obviously the major transporting medium in the desert. So, they're formed obviously by the movement of sand driven by the wind. Now, the thing about the wind is the wind isn't strong enough to actually move large clasts. So a wind can't move cobbles and it can't really move gravels. So in a desert system, if we go back to our alluvial fan, as the wind hits this sediment here, well, it can't move the coarse stuff. So the boulders, the cobbles, the gravels, well, they get left behind. The only thing the wind can move is the finer material, your clays, your silts, and your sands. And so the wind will preferentially remove this finer material from alluvial fan deposits and put it onto the desert plain. Now, once it's on the desert plain, it's still obviously being moved around by the wind. The thing is silts and clays are very, very light particles, and so they will actually get blown away by the wind and transported out of the desert system. So they get removed. And so what you're left with on the desert plain is nothing but sand-sized clasts. And obviously, over time, as the sand gets moved around, it becomes better sorted, more well-rounded, and more quartz rich, as we just discussed. So this is our basic situation. So here's a diagram of your standard desert system. So here is our source area, and this represents the coarse material that gets left behind, so boulders, cobbles and gravels. And this is referred to as the lag gravel. Now the wind will pick up the lighter material, your sands, your silts and clays, and it will transport them away. Now, the thing about the wind is capable of picking up and transporting silt and clay over quite large distances, so they get stripped out of the system and they get transported away as desert dust, which is also sometimes referred to as loess. And now these desert dusts can get transported huge distances. So, you know, every once in a while you might watch the weather forecast and they might mention that some Saharan dust is crossing the Atlantic and it's heading towards the southern United States. That's not uncommon in the slightest. And so that shows you the kind of distances that these, you know, desert winds can transport this very, very fine sediment. So obviously the gravels, the cobbles and the boulders were never able to move in the first place. The silt and the clay gets transported away, and so that means in the desert system itself the only material left will be sand-sized clasts. And as discussed, because the sand gets moved backwards and forwards across the desert plain by the wind, it means it gets transported huge distances, so the clasts get well rounded, they get well sorted, and they become more quartz rich. In terms of the sandstone layers that form, obviously because we have dunes, we're going to get nice crossbeds forming. And so here's a picture of southwestern Libya. And so we're in the Sahara in this instance. And so this is going to be our source area for the sediment. You can see it there. Okay, so that's our source area. So it's a mixture of cliffs and alluvial fans. And so what's going to happen is the sand, the silt and the clay is going to be removed by the wind from this area, and it's going to get distributed across the desert plain. Now we've also discussed the clay and the silt will be transported away, and so all that gets left behind is the sand. So if we look at this picture here, we can actually see we have a couple of different types of sand dunes. We have crescent sand dunes here, and we have linear sand dunes here that form a line. So this is the crest line for the linear sand dunes, and the nice thing about the crest line is it has to be 90 degrees to the direction of the wind. So we know therefore that our wind must be coming in at 90 degrees to the crest line, somewhere like so. So the final question we need to answer is well, which way is the wind going? Is it going southeast northwest, or is it going northwest southeast? And the answer to that is actually quite straightforward. It's got to be northwest southeast because we know this is the source region here. Therefore, we know the sediment must be being transported this way onto the desert plain. So we know that the prevailing wind direction must be from the northwest to the southeast. So what about Playa lakes? Well, Playa lakes are temporary bodies of water that form on the desert plain. So they will be sporadically replenished if there's a heavy rainstorm, but most commonly they tend to form during the spring when you get snow melting on the nearby mountains. The lake itself will obviously evaporate away because what you have is you have a body of water in a hot, dry environment, and the water that's being lost to evaporation is not being replenished. Because remember, it only gets replenished sporadically. And so this means obviously we're going to end up forming evaporite minerals. But before we start depositing the evaporites, the first thing we're actually going to get deposited is a sequence of laminated muds. So the water enters our lake, The water obviously then comes to a stop. That means any fine sediment in our lake water will then be deposited. So we get clays and silts being dropped, so that forms a laminated mudstone. And then the water on top of it begins to evaporate away, and that's when we get the deposition of the evaporite minerals. So we'll start seeing minerals like gypsum, which is calcium sulfate, we may get some halite, which is salt, and we may get a whole range of other minerals, things like the boron minerals, like borax, might start to appear. So this means that Playa Lake deposits tend to be associated with this kind of white looking material. These are the evaporites. And so once again, here's our high ground. Here are the alluvial deposits. You can actually see them in the foreground of the picture over here, and you can see them in the background there. And so this area here represents our desert plain, and you can see this is our Playa Lake. So the lake margin itself comes all the way around like so. Now you'll notice though, obviously the lake itself is here, so that means the area that was covered by water here, this water's evaporated away, it's been lost. And so the dissolved minerals in that water have been deposited as the white evaporites that we can see here. And so this is a standard Playa Lake system. You know, over time the water will continue to evaporate away until all you're left with is just evaporites. Then there will be another rainstorm, more water will enter the system, cover the evaporites. The evaporites will be protected though, because what will happen is as the next flow of water comes in, it will then deposit a layer of mud that will cover and protect the previous evaporites. Then obviously that water will evaporate away, producing another layer of evaporites. Then the lake refills again, you get another layer of mud, then another layer of evaporites, and so on and so on. So you get these repeating layers of mud, evaporite, mud, evaporite, mud, evaporite, etc. So the final continental setting we're going to think of are glacial environments. So sediments deposited through glacial processes are collectively referred to as drift. And glacial sediments themselves are separated into two distinct types of drift. There's till, which is a very mud-rich conglomerate. So most of the time when you see conglomerates, they tend to be dominated by, cobble and gravel-sized clasts. Well, in the case of a glacial till, there are cobble and gravel-sized clasts. However, they are separated from one another by large amounts of clay and silt-sized material. And so what you have is an extremely muddy conglomerate, which is very, different from your average conglomerate that you might get in, let's say, a braided river system. Your glacial tills are going to be poorly sorted, so you can have size ranges from boulder to clay. And they are typically non-stratified. That's because the glacier just dumps the sediment. It doesn't actually, there's no process going on that's going to sort the sediment and produce nice sedimentary structures. So the bodies of sediment that are formed as the glacier melts and dumps the sediment are referred to as moraines. Now, obviously, because a melting glacier will produce quite large amounts of water, that water that's produced as the ice melts will obviously erode and redistribute some of the glacial till. And this produces a range of sediments which we refer to as outwash. So outwash sediments tend to be sand and gravel dominated deposits. The reason is that the coarse stuff, your boulders and your cobbles, they can't really get moved too easily by the water, so they don't really get transported away from the moraine. The clay and the silt gets obviously washed out of the area by the water, and so that means the sediment that gets left behind is dominated by sand and gravel. Now, most outwash systems are actually braided river systems. So we've already gone and discussed the types of things that we would expect to see, because an outwash system is going to give us the same appearance as a braided river system. So here's our glacier itself. So the glacier is snaking down, and the glacier is melting right here. And you'll notice we have this pile of sediment. So this is our moraine, and our moraine is going to be made of our till, our very muddy conglomerate. Now obviously the melting ice is going to produce quite large quantities of water. This water is going to transport sediment off the moraine and onto this area here. So this is our outwash, which is our braided river system. And so what we're going to get is we're going to get the deposition of gravel and sand-sized clast material here. So we're going to get conglomerates forming in this area and sandstones. And the mud and clay, the fine material, will be transported out of the system and further downstream. And so you'll see we're going to get these two distinct types of environments. We're going to get a conglomerate here which is dominated by muds and silts, whereas here we're going to get a set of conglomerates and sandstones that are going to be almost mud and silt free. So I should say clay and silt free, sorry. So the braided river systems obviously rework the moraine deposits and often cut through them. Now, the presence of drift sediments can be used to infer a glacial environment, so they're very helpful. So once you see a rock that looks like a glacial till, you can say, yeah, that's probably due to a glacial system. However, what you really want is you want a little bit more evidence, just so you can definitively back up your environmental interpretation. So there are a couple of things we might look for. The first thing we might look for are striated and polished bedrocks. So if we look at this picture here, what you'll notice is we have this very smooth rock outcrop that has these big, deep gouges in it. So these gouges are striations, and they're produced as pieces of rock which are stuck in the bottom of the glacier get dragged over the exposed rock. And so they cut these big, deep grooves as they go. Now, I'm going to be honest, these striations that we see here are very extreme examples. Most striations are just like, scratches on the surface of the rock. These ones are particularly huge. But the basic principle is nevertheless the same. So we're going to look for rocks which have these striations on them. So you get lots of lines all running parallel to each other. The other thing you'll look for is this polished bedrock. So this is the rock that's exposed as the glacier moves over it. Because remember, the glacier is going to be like a bulldozer. It's going to clear away trees, it's going to clear away soil, any loose rock will get removed by the glacier, and so the glacier itself will move across the exposed bedrock. Now, in the bottom of the glacier, we not only have big clasts like boulders, cobbles and gravels, but we also have finer material, sands, silts and clays. And so the sand, the silt and the clay, as it rubs over the bedrock, it's actually going to polish it. And so what happens is your sands, your silts and clays end up smoothing out the bedrock and producing this very polished appearance. Your larger clasts, your gravels, your cobbles, your boulders, will be dragged across this polished bedrock, cutting these striations as they go. And so if you can find something that looks like a glacial till, and if you can also find that it's associated with these polished and striated bedrocks, well, then you have absolutely brilliant evidence to suggest that what you're looking at is a glacial system. Another thing you can also be on the lookout for are U-shaped valleys. Now, U-shaped valleys tend to be associated with glaciers that formed not long ago, so they tend to be relatively young features, and they are only associated with alpine glaciers, the types of glaciers that you get in mountain ranges, the ones that look like rivers of ice. So if we actually find a U-shaped valley, it looks like this. So here you can see the very distinct U-shaped valley morphology. You can see it here as well. So a U-shaped valley tends to have quite steep sides, then it tends to curve round to a flat plane, and then it comes up again on the other side, producing this rather obvious U-shape. And so this is showing us that this area here used to be filled with a single glacier, which I dare say, as this looks like the high ground, was probably flowing down towards us. And so if you can find a U-shaped valley like this, so once again you would find glacial till sediments associated with a U-shaped valley, that's another good piece of evidence to suggest that what you're looking at is a glacial system. So it's all about being able to definitively prove the sediments that we're looking at are related to glacial processes. So here we go. So this is what a glacial till actually looks like. Note that it contains very large clasts, so boulders, cobbles, gravels, but it's also a mixture of finer materials, sands, silts and clays. So this is what a lithified glacial till looks like. If you take a glacial till and you lithify it, it becomes a type of rock which we call a tillite. And you'll notice, here's our tillite, and you can see we have our nice rounded clasts. So we have, what probably look like cobble and gravel sized clasts here, in a matrix that consists of a lot of clay and silt. So it's quite a muddy matrix. And so what we have here is the kind of classic appearance of a glacial till. It's a very muddy conglomerate. Okay, so I'm actually going to go back several slides and we're going to very quickly look at the type of sediment we get from a braided river system. So here we go. Compare that to the braided river system sediment, which you'll notice is, once again, it's a conglomerate, but it's dominated by our cobble and gravel sites class. There's practically no mud or silt present. So the fact we have all of this mud mixed in with this conglomerate is a very strong indicator that what we're looking at is a glacial sediment. And obviously the glacial till itself will build up along the edge of the glacier where it's melting. It will form this pile of chaotic sediment, which we refer to as the moraine. And obviously the meltwaters will redistribute some of this moraine sediment to form the outwash plain, which consists of braided rivers. Now, if you happen to form a glacial lake, you'll get a rather distinct sequence of sediments. So once again, if your glacial ice water, meltwater, happens to get trapped behind some kind of barrier or in some kind of depression, the water will obviously build up, forming a lake. Now, the interesting thing is that these lakes will get filled by alternating bands of dark and light sediments. The dark sediments are more mud-rich, the light sediments are more sand-rich. And these light-dark couplets are referred to as varves, and they're a kind of classic indicator that what we're looking at is a lake system, and they are very, very common in lakes associated with glacial systems. So you'll get varves in normal lake systems, but the best type of environment to form a varve will be a glacial system. So each varve represents 1 year's worth of accumulation. The light layers represent spring and summer, and the dark layers represent autumn and winter, or should I say fall and winter. So the light layers represent a time when your lake isn't frozen. That means the wind is moving around the water, so your lake is, it's a low to moderate energy environment. And this means that fine material like clays and silts will be held in suspension in the water. They will not be able to rain out onto the bottom of the lake. This means that any sediment being deposited in the lake during the spring and summer is going to be dominated by coarser class, mostly sands. Now, when the winter comes, temperatures drop, your lake will begin to freeze over. Once it freezes over, obviously the water is no longer being moved about by the wind, and so all of a sudden your water becomes near stationary. And obviously once your water is near stationary, all of a sudden the fine material, the clays and the silts, can begin to exit suspension and form layers on the bottom of the lake. And so we get this distinct difference between the spring and summer and the fall and the winter. And we can see this as these different layers. So we can see this light layer here represents the spring and summer, and this darker layer here is going to represent the fall and the winter. Now, one of the other things that we get associated with desert systems is we get icebergs. Now, icebergs can be small, they can just be little pieces of ice that break off the glacier and float off into a glacial lake, or sometimes they can be absolutely huge. They can be, thousands of square kilometers of ice which, break off and snap off the edge of places like Greenland or Antarctica. So, an iceberg is simply a chunk of ice that breaks off the edge of a glacier. And this will occur when your glacier reaches the ocean or a large lake, and that's simply because the ice will leave the land and it will start to head out over the water. Now, as we know, ice floats, so you'd think the glacier should be able to move across the water quite easily. The problem is, of course, glaciers are quite big and bulky, and so as the ice tries to start to move across the water, the natural weight of the ice will start to pull the ice down into the water, and obviously that will mean the ice will eventually snap. And when it snaps, that's going to mean bits of it break off to give you icebergs. Now, the icebergs themselves don't just consist of pieces of ice. There's going to be sediment mixed in with that ice. And so as your iceberg moves away, it will steadily start to melt, and as it melts, these pieces of rock will fall out of the ice. Now, most of this material will just tend to be quite fine material, sand, silts and clays, so nothing particularly interesting. However, some of the class sizes can be quite large, gravels, cobbles and boulders. And because these icebergs can actually travel quite large distances, it can sometimes mean that you'll get these random lumps of quite large pieces of rock occurring in environments where they just shouldn't be able to occur. So here we have a picture of the abyssal plain of the Bering Sea between Alaska and Russia. Now this is an environment that's very, very low energy, and so we should normally expect to get pretty much nothing but very, very fine clays being deposited. However, you'll notice that on here we have these gravel size clasts here, and here we have a clast that's clearly, a cobble, which doesn't really make sense. This is a very low energy environment. You should not be able to get clasts this size in this particular setting. The reason, of course, it's there is because we've had an iceberg come through. The ice has melted, releasing this cobble sized clast and these gravel sized clasts, and then they've dropped straight onto the seafloor. These are referred to as dropstones. And so this is a modern example here, but we can also see an example here from the rock record. So here we have an example of a dropstone. This is from Namibia in Africa. And you can see here's our dropstone, and you can see that it's dropped down, and you can actually see the impact that it's made as it's hit the sediment, and you can see how it's deformed the sediment there. So once again, what we have here is we have a set of deep marine sediments. Now, they've taken on a red colour. That's due to the process of lithification. They would have initially looked like this. And this is obviously the chunk of our dropstone that's actually doing the impacting and deforming the sediment here. And we can actually even see the same thing happening here in our glacial lake sediments. There we go. We have ourselves a dropstone right there. So that's showing us a little piece of ice got into our lake and was melting and dropping, in this case, what looks like a small cobble as it went. So once again, we look for all these different indicators to show us that there were glacial processes going on. Okay, so this is a great place to stop part 2 before we move on to the transitional environment. So once again, stop the video, get up, have a walk around, take a few minutes, relax, and then come back for part 3, please.